Okay, let's dive into a really fascinating explainer today. We're going to break down exactly how Netflix manages to deliver flawless streaming to the entire world without, well, constantly crashing. It's honestly a genuine marvel of modern system design, and today we're unlocking the engineering secrets behind the whole shebang.
Just think about it for a second. Imagine millions of people across the globe hitting play, frantically searching for new shows and pulling massive data-heavy 4K video files at the exact same moment. I mean, a 4K video file is enormous. We're talking gigabytes of data per hour for just one viewer. Now multiply that by millions. How does this not just result in endless, frustrating buffering? How do their servers not literally melt down?
Because they're operating in more than 190 countries, the sheer volume of global traffic they deal with is just staggering. If Netflix used a traditional single application to run their platform, that app would instantly become a disastrous bottleneck under the weight of the entire world logging in at once. You simply can't serve 190 countries from a single central point. The physical distance alone would cause massive delays, let alone the overwhelming traffic overload.
So, to understand this engineering marvel, we're going to explore the core problem and the 5 foundational technical pillars that solve it. Number 1, the global scale challenge. 2, scaling with microservices. 3, AWS Cloud Infrastructure. 4, speeding up with caching. 5, the Open Connect CDN. And 6, designing for inevitable failures. All right, let's start with section 1, the global scale challenge, or the threat of the bottleneck. We really need to appreciate the immense pressure put on the system at any given second. Look at the sheer variety of simultaneous actions happening right now. Millions of users aren't just passively watching a screen. At the exact same time, they're actively querying databases by logging in, they're browsing endless catalogs, updating their watch lists, and initiating massive data transfers simultaneously. Handling that combined chaotic traffic, it isn't just hard, it requires a totally different approach to software engineering. Which brings us to section 2, scaling with microservices or breaking down the monolith. To prevent all this traffic from crushing a single server, Netflix had to completely rethink software architecture. Instead of relying on one massive monolithic application that breaks under pressure, kind of like a single giant highway completely choked with traffic where one accident stops absolutely everything, Netflix relies on many smaller, independently operating services that are way more reliable. So, when you open Netflix on your TV or phone, you aren't actually just opening one app. Dozens of these distinct, specialized microservices go to work behind the scenes to build your experience. One handles your authentication, another fetches your specific recommendations, another powers the search bar, and others manage your billing and viewing history. And here's why this is so brilliant. If the recommendation service crashes because of a bug, the streaming service is completely separate. You can still watch your movie even if your homepage looks a little bare. The absolutely crucial point here is efficiency, because these are all separated. If everyone is suddenly searching for a highly anticipated new release, Netflix only needs to spin up more search instances, basically creating quick clones of that specific search program to handle the localized load. They don't have to touch billing or viewing history at all, keeping the rest of the platform completely stable and incredibly resource efficient. Let's move on to section 3, AWS Cloud Infrastructure, powering global distribution. Running thousands of independent microservices requires massive computing power. Rather than being tied to a few physical buildings that they own and manage themselves, Netflix utilizes Amazon Web Services, or AWS, for much of its cloud infrastructure. Think about it. Building their own physical data centers all over the world would be incredibly slow, wildly expensive, and just a nightmare to maintain. Renting AWS cloud space gives them an instant, global digital footprint across multiple geographic regions all over the planet. This cloud computing approach gives them incredible flexibility. The system can automatically allocate computing resources to respond quickly to changing demand. Think about when a new show drops and becomes an unexpected overnight hit. The real magic here is the automatic scaling. There are no human beings frantically scrambling in a freezing cold server room to manually plug in new hardware. The code just adapts instantly, pulling more cloud resources to handle that massive surge in popularity on the fly. All right, section 4, speeding up with caching, or preventing database overload. So even with practically endless cloud power, querying the main database every single time someone in the world asks for information about a trending show would still drag performance down. To avoid crippling their databases, they rely on a really vital technique called caching. You can think of a cache as a high-speed storage layer. It holds frequently accessed information.
So when you ask for data on a popular movie, the application retrieves it from this incredibly fast cache layer instead of doing a heavy, slow database query. By retrieving data from the cache, the end result is a massive win-win for everybody. You get faster responses and significantly lower latency, meaning the delay between you pressing a button on your remote and the screen reacting is virtually zero. Meanwhile, Netflix gets a dramatically reduced workload on their backend systems. It really is one of the most important engineering techniques behind large-scale internet applications today. Moving on to Section 5, the Open Connect CDN, solving the bandwidth challenge. Okay, so we've solved the application side, but streaming heavy 4K movie files introduces our next massive hurdle, bandwidth congestion. Movies and TV shows are enormous files. Sending them from a central location to millions of homes would cause severe delays. I mean, instead of streaming a movie all the way from a server in California to a TV in London, Netflix built Open Connect. This is their very own custom content delivery network, utilizing specialized servers placed physically inside the buildings of local internet service providers, like right inside that London ISP. So when you press play on a movie, your request actually bypasses those distant central origin servers entirely. You don't have to wait for signal to cross an entire ocean. Instead, the video is delivered directly from an Open Connect server parked right in your own neighborhood. This drastically reduces buffering, improves your video quality, and gets your content playing almost instantly. Finally, Section 6, designing for inevitable failures, also known as resilience engineering. Even with the absolute best cloud infrastructure and local servers, hardware and networks will eventually break. At Netflix's scale, failures aren't just possible, they are mathematically guaranteed. Servers fail, networks go down, power goes out. But instead of assuming perfection, Netflix engineers practice resilience engineering. They actually intentionally break their own components just to see how the platform reacts. It sounds a little crazy, I know, but constantly injecting chaos and intentional failure testing is exactly what keeps them online. Their core design philosophy dictates that a failure in one part of the system absolutely should not bring down the entire platform. They expect things to break, right? So the architecture acts like bulkheads on a submarine, intentionally containing the error. If one tiny component floods, the rest of the ship stays completely dry and afloat. So, when you put it all together, what you realize is that Netflix isn't just some simple app on your TV powered by one big server. From your perspective, sure, it's incredibly simple. But behind the scenes, it's a symphony. It's thousands of distinct, perfectly synchronized, specialized systems working as one cohesive unit just to bring you a movie on a Friday night. It's an incredible lesson in modern system design, and it really makes you wonder. If simply hitting a play button requires thousands of distinct systems, global CDNs, and microservices to work perfectly together behind the scenes, what other invisible engineering marvels are quietly running your daily life right now? Thanks for joining me for this explainer, and we will catch you on the next one.